This video illustrates a structural transformation. We are watching a flat, high-density two-dimensional grid of server data collapse inward to form a three-dimensional geometric corridor. This visualizes the core diagnostic challenge for site reliability engineers, parsing thousands of linear, repetitive log lines to find a single point of failure. When systems generate constant streams of routine terminal outputs, analysts experience alert fatigue. Continuous scrolling through identical text blocks degrades attention, causing critical network anomalies to slip past unread. The human brain struggles to extract patterns from raw text at high speeds, but it is highly optimized for spatial processing. It identifies anomalies immediately when they exist in a multidimensional space. To leverage that biological advantage, we use the .doom-logs.json file format. This format acts as the bridge between raw server outputs and interactive three-dimensional environments. Doom logs serves as a rigorously structured data visualization tool. It replaces the traditional console with a functional diagnostic environment. Analyzing how this operates requires tracking a specific pipeline, starting with data ingestion and consolidation, moving through user interaction, and finishing with forensic review. Translating logs into spatial coordinates shifts the engineer's role. They transition from passive readers scanning text into active hunters navigating data, reducing the time required to isolate root cause events. The process begins at the ingestion phase, where the local compiler evaluates the raw JSON file. The compiler streams and groups consecutive events, relying strictly on identity and status. When a routine event repeats, nodes dynamically stack, generating a multiplier. This prevents recursive loops from flooding the space. 100 individual nodes creates noise, but a ×100 tag delivers exact volume instantly. Generating a new entity requires strict triggering criteria. If the system status, specific action, or primary source diverges from the previous log, the flow branches off, creating a completely separate target. Applying these strict criteria guarantees that every discrete target rendered in the environment represents a genuinely unique system state. Algorithmic consolidation functions as a high-pass filter. The engineer's cognitive load scales strictly with the complexity of the anomalies, rather than raw log volume. Once the compiler filters the data, the visual rendering engine determines how to display complex data provenance accurately. The primary event log provides the foundational color for the target, allowing instant source identification. For multi-source corroboration, secondary data arrays route directly to the existing entity, wrapping around the base shape as colored armor bands. These high-contrast bands act as immediate visual indicators. An engineer can identify mixed-source anomalies based entirely on the target's outer layer. Standard logging dashboards demand context switching. Cross-referencing multiple sources in text usually requires opening secondary tabs or running entirely new queries. By stacking colors onto a single shape, the spatial mapping preserves the exact chronological sequence of corroborating events as one readable target. Multidimensional visual provenance gives the engineer the ability to verify the scope and supporting architecture of an anomaly visually before reading a single line of text. Moving from rendering to the user interface, we encounter the need for a friction-free query system. The core interaction relies on targeting. The user's crosshair functions as a live query tool directed at the rendered entities. When a target is acquired, a compact intelligence card populates in the upper right corner of the HUD, maintaining an unobstructed view of the environment. The card surfaces precise live data points, the primary source origin, aggregate log counts for multiplier targets, and fully decoded system statuses. This layout solves a strict engineering constraint. It delivers high-density context directly to the user without causing screen flicker or interrupting the continuous monitoring workflow. The intelligence card serves as the intermediary step. It connects spatial anomaly detection with the eventual deep dive review. Zero-latency querying eliminates the context-switching tax inherent in traditional diagnostics. Engineers triage threats rapidly while maintaining awareness of the broader network environment. Eliminating the anomaly in the spatial environment serves a specific mechanical function. It isolates that specific data trend for paused review. This interface design shows the immediate UI shift. The spatial environment freezes, and the system transitions the user entirely into the kill dossier. The dossier contains the raw forensic evidence. It displays the uncompiled system events and the exact metadata CSVs mapped to the original target. Establishing this paused state is necessary. It gives the engineer unlimited time to investigate the isolated trend without the background environment continuously updating. When tailing a live log in a traditional terminal, critical diagnostic data is constantly pushed off the screen by new incoming events. Inside the dossier, the engineer verifies delivery proofs and traces the exact chronologies that led the compiler to group the events. The kill dossier represents the culmination of the diagnostic pipeline. It delivers the granular proof required to formally resolve an incident, presented only after the system has naturally guided the engineer directly to it. This flowchart maps our visualization architecture into 5 distinct phases. The first half reduces data noise by ingesting raw logs, aggregating them through multiplier logic, and rendering spatial targets. The second half handles user interaction, transitioning from high-speed spatial pattern recognition to pause data review. Effective log analysis requires tools built for human biology. Spatial mapping respects the brain's natural capacity for visual processing over brute force reading. By translating raw JSON into structured interactive encounters, this pipeline eradicates scroll fatigue. It pulls abstract server monitoring into sharp focus, transforming a wall of text into highly targeted incident resolution.